We have already talked about functions, but we can now properly define what a function is. So function is just a relation, but it has the additional requirement of being n to 1, or 1 to 1 for that matter. It cannot be n to n like we saw in the example relation less than. So function is a relation with that additional requirement. We also use the colon arrow notation to define a function. So here we see in the box, we see the function f is the function on the input set producing the output set, or the codomain. So the input set is the domain and the output set is the codomain. A function of one variable is called a unary function. Why? Because it's a function of a single variable, but it's actually a binary relation because it relates an element y to an element x in the input. So a unary function relates an element y in the codomain to an element x in the domain. And in this case, we are showing the definition with the set x as the domain and the set y as a codomain. So the function is a subset of the order pairs resulting from the Cartesian product x times y, the set x times the set y, with the requirement that there cannot be an n-to-n relation. So we have at the bottom of the slide here two examples of sets of tuples that could be the result of the Cartesian product or a subset of the Cartesian product. The first one is marked out, it's crossed out because we have the element 0 relating to the element 1 in y, and we also have the element 0 relating to the element 0 in y. So that is a 1 to n relation right there. So anytime we have one element relating to more than one output element in the codomain, it's not a function. The second example, we have two ordered pairs. We have 0 relating to 1, and we have 1 relating to 1. So now we have the opposite case, where we have two input elements mapping to the one single output. So this is 2 to 1, or n to 1, but it can be a function. That is allowed in a function. Now let's use a plot of a relation and a relation that is also a function on a set to illustrate the idea a little bit more and how they are different. So let's consider again the set X with three elements, the numbers 1, 2, and 3. And the Cartesian product is then the 9 tuples that are shown in the tiles of the images in the slide. So there are 9 tiles, and in each case the tuples, the ordered pairs that belong to the relation, are highlighted in blue. In a less than relation, the first column, by the way, in each of the two images, the first column corresponds to the x element in the ordered pair being 1, while the second column has the x element 2. But we see that for x equals 1 in the relation x is less than y, there are 2 blue tiles with y being 2 and 3. In the function, that is not the case. In the function, in this case, we have a 1-to-1 function. Each of the columns has only one blue tile in it. Now, the function we show here is a unary function. It's a function of one element, but it relates that element to an output element. That's why it's called a binary. That's why it is a binary relation. So a function is always a relation as well, just with that special restriction that one input element can only produce one output. We can, however, have two different inputs producing the same output. So we can have an n-to-1 relation, although that's not what we have here. In the relation here, we do have an n-to-n relation. The element 1 corresponds to 2 blue tiles in the column. We can also look at the last row, where the y element is 3 and it corresponds to two different input elements. So we can see the n-to-n and one-to-one relationships in this plot. So let's move on to binary functions. This is not a big leap from a unary function, but instead of having a single input element relating to an output element, we have an input tuple relating to a single output element. And here we are looking at the Boolean domain as an example. And we're also introducing the maps to notation here, which is that arrow looking symbol with a vertical line on the left side. So a unary function was a binary relation, and we can say that x is an element of the Boolean domain here, and it maps to an element y also in the Boolean domain. So the function is a subset of tuples in the Cartesian product b times b. Now a binary function, let's also define a binary function on the set of Boolean numbers. We now have input tuples x and y. So the order pairs x, y that are elements of b squared. These are our inputs. And this is now a ternary relation. So each one of these inputs is related to an output element also in b. So a binary function is a subset of the Cartesian triple product. Let's review a little bit, and we'll use again here the set x with just three elements, numbers 1, 2, and 3. We had previously defined the relation x is less than y as the set of three ordered pairs 1, 3, 1, 2, and 2, 3, subset of the Cartesian product x times x, where the element x is less than y in the ordered pair xy. This is not a function because the element x is 1 relates to two different outputs, 3 and 2. Y is 3 and 2 in this particular relation, so this relation is not a function. We talked about binary functions, so we just shown a binary relation. A binary function is actually a ternary relation because the function produces a third element z, which is the output of the function. So we're using here the example plus x plus y is our binary function. Our binary function is the function x plus y producing a third element z as the output, so z equals x plus y. Therefore, our function is a subset of the triple product, Cartesian product of the set x. Now all we're doing here in addition is defining this function only on a specific domain, a specific subset. And let's look at the bottom portion of the slide. Again, we're using here the maps to notation, so we have an input element mapping to an output element. In this case, our input elements are the ordered pairs x, y, which are a subset of the Cartesian product x times x, mapping to a single output element z in x. What we're doing here in addition is defining our input, our domain of our function as a specific subset of the Cartesian product of x with itself. So we're defining our domain to only have three ordered pair input elements in it. The ordered pairs 1, 1, 1, 2, and 2, 1. And we're doing that because additional elements, ordered pairs with higher numbers than produce a result, a z number that is not in x in this case. But we can define our plus operation any way we like. So the result is x plus y, the function is a subset of the triple product x times x times x, and we've written out the actual set, so the function is actually equal to the set of three triplets, 1, 1 producing 2, 1, 2 producing 3, and 2, 1 producing 3, subset of the Cartesian triple product of x. So all we've really done here is define a function on
a specific domain and use our set notation. We've written out the actual sets rather than what we've seen typically before, were cases where the function was defined on the entire domain. And as a result, our function definition at the bottom of the slide here, plus colon domain right arrow codomain. Our domain here is specifically the set of order pairs 1, 1, 1, 2, 2, 1 in the Cartesian product x times x, and our output x, or our codomain, is specifically the elements 2, 3 in the set x. Let's summarize what we covered in the session. We started talking about relations and showed that a relation is nothing but a subset of the Cartesian product. We talked about relation between sets A and B as a subset of the Cartesian product A times B. We also talked about relations on a set and inverse relations. Then we defined a function as a relation with the additional rule that it must be n to 1. And we talked about binary functions and showed that they are ternary relations. They are subsets of the Cartesian triple product. And we spent a little bit of time comparing relations and functions and looked at some examples of each.